of important definitions. So we call this diagram a tree diagram, and this idea where you draw a space for every decision you make and number of choices in each one, the fundamental counting principle. They have it in your notes here, but sometimes when it's written out, you could read this and go, yeah, I have no idea what they meant. It says if there are n1 different objects in one set and n2 different objects in a second set, then the number of ways of choosing one object from each set is n1 times n2. I'm going to describe this as you draw a space for each decision that you need to make. We're going to do questions where you're at a restaurant, you have a choice of drink, you have a choice of what your meal is, and you have a choice of dessert. If they have 5 drinks, your number of choices for drinks will be 5. If they have 8 main courses, your number of choices are 8. And if they have 4 desserts, your number of choices would be 4. And you'd multiply those all out, and there would be 160 different meal combinations possible. So you could go to that restaurant 160 days in a row and not have the exact same thing twice. So the idea being that your number of choices go in the space and we make a space for each decision. So we go here to example 1. This example always reminds me of my brother because I don't know when it started, but he had a fan when he was young to sleep, and now he can't sleep without a fan. So like even if he goes traveling, he brings a little fan along because he needs that air movement, or I'm not sure what exactly it is, in order for him to sleep. Okay? But here this is like next level. You have 3 different fans set up in different places in your room. You can get a different experience for sleeping. We're going to find out how many. Okay? So if you had 3 fans, if we did this the easy counting way, you have 3 decisions to make. Fan number 1, how many choices? 3 choices. Fan number 2, how many choices? 3. Fan number 3, how many choices? 3. There's the fundamental counting principle. It allows us to count things very quickly, even though numbers can get big, 27. If you had to list them all, the tree diagram would probably be off, low, high. It's a little bit, right? You wouldn't want to do too much more than this. It's off, low, high. Off, low, high, off, low, high, and then off of each of these 3. Fan number 3. Oh my goodness. This is what it is. I'm running out of room. Off, low, high, off, low, high, off, low, high. I mean, this tree diagram, if they asked you to write out all 27 different possibilities, this would be the way that you could write them all out, right? You want a super calm night, you can go with this one. Ooh, right? Ooh. Right? And then there's like, oh, if you want a little bit of fun, you can have like this one. Okay? There we go. And so you could list, I mean, this would allow us to list all 27 of them in a systematic way. Whereas if you tried to just think about them, you'd probably get lost. Which ones it would take a long time just to think about them. This is nice and systematic, but it's annoying as a way to count them. The fundamental counting principle really lets us count it quickly. We had 3 decisions. How we want our fans on, right? So turn this one on, this one off, this one on. You could almost go a whole month with a different wind ambiance in your room going to bed before you'd have to have a repeat. Okay? So what we're going to find out is the questions that we're going to get are going to be weird word problems. And you have to read them, analyze them, and say, okay, how can I use the strategies that we're learning to figure them out? Right now, I'm going to give you a bunch of questions, but they're going to be relatively easy because we have only learned one strategy. They will get more difficult when we learn other strategies. But right now we've learned the fundamental counting principle. You need to make a space for every decision. And in that space, you put the number of choices. And then multiply them together to find out the total number of possibilities.